But that's stretching it because you don't know if he's going to come early or late. What's wrong with ice?
Oh, yeah, of course.
For me, I got a midterm at 12 tomorrow.
Okay. Okay, I think we need to start. And what I wanted to do today is I will review what we covered last week. I'm going to also cover some other material that I covered yesterday. But before we go there, and then I will solve some problems. Before we go there, however, I wanted to speak with you about how, you remember I told you that I was going to look at every student's progress? I wanted to show you how I can see things individually. This is from last winter, all right? So last winter, what you see on these graphs is that I can find out how many times you access the material on Canvas. And then these are communications between me and the students, and then it shows, in fact, whether you got, what grades you got. The green means you are in the top 25, 30%. Yellow means that you are going close to 50% in terms of the average grade, I mean, and then red means that you have been below that. But I wanted to show you that this is what I mean by high A. That was a grade, the first A next to the A plus group, all right? That's how you show this individual had a continuous through the semester, continuous work. It was not coming in spikes around the quiz or the midterm or the final, all right? So this continuous work is beneficial and eventually is going to lead you into a very successful outcome. Now, I'm going to show you then, so look at this, the number, right? That shows about 100, maybe that was this individual in the first quiz. And then you see how, because the person was able to learn more and more, you don't see a spike, that big of a spike in the midterm or that big of a spike in the final. But look at then at someone else from the same class, and that was a C+. But look at in the beginning, and this shows, you know, the page views around midterm. The midterm is this huge spike above everybody else, but it does not help if you leave things behind for a long time and then you go around the midterm and kill yourself or in the quizzes, and then you leave things again and then you come back when there is an exam. You will never be able, unless, of course, there are exceptions. So I'm talking about the average person, because there are exceptions to the rule. There are people who are the 3 sigma, all right, from the distribution. You saw, however, how the grade there were, the reds mean below or no submission. The yellow ones with a spike showed late submissions, even if I accept the grades and so forth. You see, in fact, the progress of this person. So I'm in the process of looking at ours. And so now, I'm showing you, if this is very early, obviously, but I'm showing you a person whose progress I would characterize as very good. Good progress, meaning if this person continues the same way, I think the grade is going to be good. And you see the continuous, in fact, from the page views and everything. I don't remember what the blue shows and what, but in any case, it shows whatever interaction the student had with Canvas, with the material, obviously. And then you see how this person has met all of the, you know, the deadlines and got a good grade for each one of them. I will then show the case of one person who needs to change studying habits. And it's like that. This is the person, and I'm not saying you don't know how many points. These are not necessarily few points so far. This is not the last person in class, but it's a person who only studied around the meter, and then after that, there was little before, little after. Look at all of the delays in the homework, even if there is, and I will speak about the delays next. And then this person, if continues like that, the grade is not going to be good because the class gets more intense. And then you cannot assume that you will learn everything that 1 week that you have a final or that few days around the meter. So, and this is just, I have not looked at everybody. I cannot tell you how many people are on the same, but if you are on this kind of studying schedule, regardless of the points you have, don't get confused between how you study and the points you have so far. You may have enough points to make you satisfied, but if that's your studying habit, things will not go well. Because this class needs continuous attention to the material. Then I will show you something that an individual, and I don't know how many like that, who I would suggest changes their attitude. So, and this is this one. Excuse me, the next one. All right. And I will tell you why this is problematic. You see all of these lines? All of these lines are the surveys. So I'm giving you the survey to recognize 5 points, to recognize that you are taking some time every time there is a survey within, and I give enough flexibility in the surveys, all right? I even accept them if they are reasonably late because I value your input. But if the survey in this particular case was given October 3rd, and the person filled it out October 25, what did they remember from the lecture? So obviously, I did not get any information that was meaningful, and it was only an attempt to get a grade. Now, I so far have not removed this. I have not removed anything. I have not done anything. I just watch it, all right? So I will see how this individual goes. If there is a time when I need to make up my mind about an A minus, a B or a B plus, or a B minus or a B, if you are at that point. Because if you are well within a region, you know, I'm not going to remove people. If they are well in the middle of B, I'm not going to give them a B minus because of that, obviously. But if they're somewhere between B and a B minus, that is going to play a role. So what I will do after I after I look at all of those, I have not done everybody's yet. The people I worry about, I will probably connect with you. Would you like to have your individual yourselves? Because can you see those on Canvas? Okay. Would you like to have each one of your individuals? Okay. You will give me some time to do that, all right? Because I will have to download the material and so forth. Those that I worry about, I will ask you individually to come and see me. And you may have to give you advice. Don't do this like that. Do something else, all right? I'm not going to, if I ask you to come and see me, that doesn't mean that I'm going to try to penalize you for anything, all right? I would like to sit down with you and see, is there anything I can do from my end to help? That's number one question I'm going to ask you. Because the grade comes second in my mind. If you learn, I'm very generous with grades. If you learn, I will be. In fact, the lowest grade in winter was C+ for a class like this. But the kids worked really hard. And even the C+ person, at the end, you know, he tried to work at the end. He took all of the, whatever we were giving in the class, he took it. And I appreciated that, because at the end it's work. But anyways, I wanted to show you what I'm looking at, what information I have, and I'm trying to give you advice on how to, what to do and what not to do. So any questions about this? Okay. We are going then to, let me see. All right, summary from previous lectures. And we'll talk again about magnetic materials, boundary conditions on conductors and dielectrics, and then we'll solve some problems. But we are not, it's going to come as a summary. So what we've learned about magnetics is that if you have a magnetic field, like a half space, all right, obviously, because you cannot have the full space being magnetic. That thing does not exist. It's not a realistic assumption to make for any problem. The only assumption you can make is that your full space can be empty, like with epsilon, like empty space or air, epsilon naught, mu naught. That's an assumption. But you cannot assume that all of your space, like the full infinite space, is magnetic. So the next possible assumption is to assume that you have a semi-infinite space, all right? So a layer material that, if this is free space, this is then magnetic. So that is a responsible assumption. Then we talked about the different types of magnetics. We said the diamagnetic and paramagnetic are the ones we look at. And ferroelectrics, of course, later, we'll talk about them. They're very useful in toroids and solenoids. And for those, when we look at them, we are not going to include in our mind the saturation issue yet. We'll assume that they perform like any other magnetic material, with the exception that mu is going to be very high. Okay? For paramagnetic, mu is not that high. Will be higher than mu naught, but it's not going to be 1,000 times higher, like it is in ferromagnetic. So let's assume you have that. Then we learned, we at least discussed last time, then when a magnetic field is exerted, like this, or any other magnetic field, could have this, all right, direction. If a B field is exerted like that, then this material creates small circular currents from the spin of the electron. Now, volumetrically, that is incorporated here. The impact, the volumetric impact of those spins that are generated and aligned in the material, which we call then the phenomenon magnetization, is incorporated here. Okay? So even if you know what happens macroscopically in reality, in physically, macroscopically, we don't care about these individual little circular currents because all of the impact is here. So we solve this problem like a problem of two materials, one with epsilon naught mu naught, another with epsilon and mu. Even if it is true that physically there are currents floating up here, but since the whole macroscopic, volumetric, and surface phenomena have been incorporated here, we don't worry about those. Okay? So that is how we address this problem. Then we said, let's consider a similar problem, but now we have free space here, and then we have a perfect conductor here. And we said that in the books, some talk about perfect electric conductors when the electric field is 0, or perfect magnetic conductors when the magnetic field is 0. But for us, we're going to talk about a perfect conductor no matter what fields we have excited, and then we will know that those fields do not exist in here. But if you have a perfect conductor, you're going to have a surface current just on the surface of the conductor and 0 fields in here. Of course, in this case, since we have a B, all right, we're going to have B0 here in the perfect conductor. Now, how are we going to explain this surface current? How are we going to explain it in conductors? The same way we explain the electron spins here. And what happens, as I said last time, is the free electrons in the conductor, in the presence of a magnetic field, they start rotating circularly, all right? Because every time you send a charge, and then it happens to go inside the magnetic field vertically, so all of the electrons that they see this magnetic field, but they are coming into it vertically, will start rotating on a closed circular path. And when an electron rotates constantly on a closed circular path, creates a current. And all of these currents will cancel each other with the exception of the surface. So in the case of perfect conductors, we have to incorporate the surface current, which we do not here, all right? Because we take into account all of the surface, all of the physical effects at the macroscopic level within nu. But since here we don't, everything is 0, and then we cannot work with this material, since everything is 0 here, we are incorporating the surface current. Is that clear so far? Okay. So having said that, the next thing we have to do is to find out what are the properties that relate this magnetic field with this current here, obviously, since there is no magnetic field there, and what are the properties that relate this magnetic field here, let me call B naught, with this one here. Because obviously, since this material has a non-zero field, magnetic field, we are going to be here B equals whatever it is, non-zero. So in this particular case, we need to find the relationship between this and that, while in this case, the only possible relationship is between this and this. Okay. So now, they, to derive those relationships, I'm not going to derive them today, but to derive them, we have to start from what, especially here. To derive this, you have to start from this equation that we know. That tells us that the magnetic field on the surface of this conductor, because there is nothing here, only the magnetic field on the surface of this conductor is connected with the surface current density. So the magnetic field intensity vector, to be precise. So the magnetic field intensity vector of this field right here on the surface is related directly to the surface current. And what we find from this, if we integrate around a surface, we find that if n is the vector that shows the direction of the surface, which is outward from the conductor, then this one gives us this relationship on the surface of the conductor. Okay? This is an important relationship. Why? Because now I can find the value of this if I know H. If H is the generating current, I can find it. If J sub S is the generating, if H, I said, is the generating field, I can find J sub S. If J sub S is the generating current, I can find H. So for example, this is what we call reciprocity in electromagnetics, all right? So if I shine a magnetic field on a conductor, and then I know exactly how this magnetic field is, then from the value of this magnetic field intensity vector, I can find the surface current. The reciprocal then statement is that if I know this surface current density, and it might be produced by another source, but if I know that, then I will be able from here to calculate H, which is the magnetic vector, the magnetic intensity vector on the surface of the conductor. Any questions about that? Yes? The reciprocity. Then, for one more. Here the field is 0. The other relationship we also find, because you need both of them, is that the inner product between this vector and B is 0. So, on the surface of the conductor, the normal component of the magnetic flux density is 0. Okay? So practically, on the surface, very close to the surface of the conductor, this is the only thing you see, a tangential B. That's important. Now, we need to remember the dual problem. What is the dual problem to that? A conductor, but with an electric field. All right? So in the dual problem of the conductor with the electric field, do you remember the boundary conditions? That the tangential E was 0, but the normal D was equal to the surface charge. You remember that? So try to, so here, I will write it here so you can, the duality between the two is important. So this is a perfect conductor. So now let's assume a problem that we have seen before. All right? We've seen it in electrostatics. If you have the same conductor, perfect conductor, but now you have charges here. So you have a charge density, rho sub s, on the surface, obviously, because that's where, and then can be positive or negative, all right? If there are electrons, will be negative. So for example, if there are electrons here, let's assume that all of these electrons, instead of creating circular wires, come here. If there is a lack of an electron, means the electrons have moved, and then those will be holes, will be positive charges. But let's assume that these are your electrons that are here. Now, what do we know from here? And this is electric field, or D or E. If this is N, then we know that E tangential on the surface of the conductor is 0. And then we know that N dot D, in this particular case, is negative charge, so the negative sign is going to be within the charge, is rho sub s. Okay? Where rho sub s needs to have the negative sign of the electron. So these are dual. They look similar, but they are not. So they are the duality. So let's go now to this, which is an air magnetic interface. we have an air magnetic interface and there is nothing accumulated here on the surface. What are the boundary conditions? Let's assume that this is N. If it's N, then the boundary conditions are the following two. N cross. Let's assume this is 1, region 1, and region 2. So we'll say H naught, region 1. So you put, if N goes upward, you put first one, the region towards N goes. If you don't follow that convention, then you're going to make a mistake in the sign. Okay, that's why that is critical to remember. Minus H equal 0. Then what else? The normal component of B 0 minus B is 0. These are the two important boundary conditions for this interface. Let us now try to see what would be the dual boundary conditions for an air dielectric interface. So here we have air dielectric. Epsilon naught, mu naught, and then here we have epsilon mu naught, all right? So here we know that the electric field, no, this is dielectric. It could be anything, all right? Could be like this. So E and D could be like that. The same thing there, as a matter of fact. It could have any direction. The boundary conditions here, if this is the N, are the following. N dot D 0 minus D equals 0. And tangential N cross E naught minus E is 0. All right? This I suggest you remember, because this gives you the only possibilities you may have, or any combination of the two, in terms of boundary conditions. You can have either air or a dielectric with a magnetic. You can have a magnetic with a magnetic. It does not matter. You can really change these to epsilon 1, mu 1, epsilon 2, mu 2. And by doing that, you can have any materials to come in contact without any sources in between the materials. Any current or any charge additional. All right? It is only on perfect conductors where we have to incorporate either the surface current or the surface charge that is generated by the electrons. In this case, because the electrons move under the electric field and they all get stuck on the surface and they stay there. And in this case, because they start moving under the magnetic field, but they create those loops. And the loops that are on the surface, they all align. Or the loop, the part of the loop that goes to the surface. All of those loops, they're parts that come to the surface, they all align and they give a surface current. Yes? It's all incorporated in this. And we normally don't derive that, we are given this number. The extra, what you may ask is, what if I place here a charge? I do. Forget about the two materials, but I have already placed a charge there. What's happening? That's a different one. We're not going to cover it now. Or one step at a time, all right? Or what is going to happen if, in this one, excuse me, I go and place a surface current, but that has nothing to do with the material. I just place it. then we have to modify these equations. Yes?
For the perfect conductor, if instead of inducing a magnetic field, we induce the surface current, would that result into that same magnetic field, or do you have?
If on this conductor, in addition to what the electrons will do, you introduce your own charge, and then there is an electric field,
No,
there is no electric field.
There's only
It's like in a capacitor.
We're just inducing a current. We're not inducing any magnetic or electric.
Or you put, yes. So for example, in interconnects. In interconnects, you already have developed a current, and then you have a line that carries it. And this current is going to flow on the surface. This is going to generate this field.
That same direction, not the actual.
No, it's going to be coming out of this. This is where I said in this particular case, this is the generating current. If it is like interconnect and your current comes like this on the surface of the conductor, this current will do two things. Will excite electrons no matter what, and also it's going to create the magnetic field. But all of this is going to come out of this relationship. Okay? So these simple relationships, this is what you're going to use if you have any material with conductor, air conductor, any material with conductor, and this is what you're going to use if you have any type of material with any other type of material. For electric and magnetic fields, magnetic and electric fields. All right? Okay, now what I want to do is to show you some other formulas that I would like you to remember. And I have uploaded those on Canvas, so I want you to have those formulas available. For all the kinds of exams you take, midterm and so forth, or homework or anything else. Okay, so let's go to those. I will show them to you and I will explain. Observations. Let's see. Okay. What I did was, can you see those or they are small? Okay, you will, yes.
Actually, what is H?
What do you mean, what is H?
When you said del crosses H equals to JS, what are those directions?
This one.
Yes.
This is del. This is H is the magnetic field intensity vector. J sub S is the surface current density vector.
Don't they have the same direction?
No, because of this cross.
I mean H and JS.
No, because they have this cross product. Whenever there is a cross product, there is a change in the direction. It's the inner product.
So what is H?
What do you mean, what is H? H is the magnetic intensity vector.
And how could you explain why?
Okay. You want me to, in other words, give you a very specific example. Is that what you want? Yes.
Just give a definition.
Like a formula definition is what I think she's asking for.
Formula definition for that?
For H vector.
Oh, how can you give a formula definition for a vector if it's general? What do you mean a formula definition?
How do I know what H is? You give me an
Okay. All right. I give it to you. I can give you that H is and Z. Let me erase some things. Okay. I can give you that H is H0 A sub y. I have a problem and I give it to you. Then you would like to find this surface current, all right? So the surface current, in this case, N is going to be Z along the Z direction. So this one is going to be AZ cross A sub y H naught equals J sub S. How much is AZ cross A sub y? Minus A sub x. Okay? So your J sub S is on the surface H minus H naught and along the x direction. So practically minus, so if this is positive and it's like this, then J sub S is going to be like that. J sub S is going to have.
That's not the negative x direction in your question.
Sorry, on the other one, yes. Like, okay. Yes.
And don't H and B have a similar relationship to our electric field and our
B is mu H. They have the same direction. And there is only a scalar. So in this case, your B is going to be the same like with H. So if this is, if I do this in a different way, let's do that like that. So this comes out of the wall, all right, positive x direction. So this is going to be negative like this. So B is going to be mu H naught, and it's going to have the same direction because of this one. Was this your question?
Yeah, when I saw the graph you draw, it's like H has the same direction as JS, and I didn't know why.
Okay, I got it. All right. So yes, it could be, for example, no, they, of course, they're not going to have, they're going to have different directions because of the cross product. It was a bad graph. Any other questions on this? All right, so we're going to solve some problems on that one, and then we're going to be more specific, all right, in the relationships. Okay, so what you see here is we have on the left side point charge, we have electrostatics. On the right side, we have magnetostatics. And I tried to put the formulas that we have derived in this class for electric charges and for electric currents. So electric charges generate electric fields. Electric currents generate magnetic fields. And what you see is that there is a similarity in the formulas. All right, so the first one, if you have a point charge and then an infinitesimal section of a current, then what you have there is, in the case of charge, you generate an electric field that varies as 1 over r squared. In the case of the infinitesimally small current, you have a magnetic field that varies also as 1 over r squared. where r is the magnitude, all right, of the distance between the charge in the electrostatics and the observation point, or the infinitesimal current in electric currents and the observation point. Then you go to an infinite long charge, and then you can look at the infinite long wire. The infinite long charge generates an electric field that goes along the radial direction and varies as 1 over r. In the infinite wire, it creates a magnetic field that goes along the phi direction, so it closes like a, in the charge it goes all the way out like that. In the current that is along the z direction, it circulates around the magnetic field like this, closed loops, but it varies on each one of these loops, it varies as 1 over r. So the closer you go, the stronger it gets, obviously, to the source. Then I also included the circular loop because there is some kind of duality, or reciprocity, I should say. There is some reciprocity between the circular loop and the infinite wire. So that's why I put one next to the other. The infinite wire creates a circular loop in the field. A circular current or a circular wire is going to create a field that is not exactly along the z direction, but it's strongest along the z direction. So I have to draw it here. So let's assume that you have a circular loop. So I will show it like this. This is the z-axis of the loop. It goes through its center, and it's also called the axis of the loop. And I can also show the loop like this from a side view, all right? That's its axis. So let's assume that the current here goes like that. So it goes like this on this side, and backwards here, the other side. Then the magnetic field goes, we always use the right-hand rule, it will go like this. It will go like this. And so forth. And these lines close far away. Okay? So in here, it's going to show like that. All right, and so forth. What that says is the following, that in a circular loop, you don't quite have a z-only directed field, but along the z-axis, the field has the strongest value. And as a matter of fact, if I were to plot the field on this loop, to plot the value of the field on this loop, all right, and this is how I will plot the value, it would go to 0 here, and then it's going to go here like this. Now, how smooth this transition is going to be, and how high this point is going to be, and how abrupt this change is going to be within the loop, it depends, of course, on the size of the loop. All right? So many times, especially as you will see in toroids, we'll assume that a loop like this, if it's small, or a loop like that, practically generates a field which is mostly included here. And for the purposes later of looking at magnetic fields in toroids or solenoids, then this is a good assumption. All right, that outside of the loop is very small, so practically 0. Inside of the loop, the value is what we need. But in reality, it's not exactly going to 0 right here. All right, it goes to 0 as you go away. And why does it happen like this? Why does the field of a loop goes like that? Because of the following reason. If you have this loop, this is its center. This is the current. So the current here goes like that. The current here goes like this. So for this current, the field comes out here from the board. And for this current, also it comes out from the board. So these two currents inside here concentrate, they add their fields. The same thing applies to this one, and the same thing applies to that one. So all of these currents, for all of the magnetic fields they radiate, they generate, they all sum up here. Now, if you go away from this point, they are not going to sum up with the same value, but they will still sum up. They're going to all be adding. When you move away from the loop, when you come here, this is what is happening. This one, for this part here, is going to go into the board. So for this current, it's going down into the board. For this current, comes out of the board. So instead of adding, they are subtracting. And that's why the value goes low. And that's why we have this kind of, and that happens everywhere outside. They only subtract outside, and they only add here, all right? So that's why the field inside is very strong and outside is very weak, and that's why we go into this ideal case. Okay, that's what we need to remember. Let's go to the next one. Okay, here I gave a section. It will be, I don't know how easy you're going to see that. Now I'm looking at the, so I may need to redo it because it does not look it's not very clear the way this copy was made. But I will also print something on and put it on Canvas about this particular case. Here is what they gave us. They gave us a section of a current, in this case, from A to B. Not that it is real. This is only a step to help us solve more real problems. But this is how, if we could assume that there was such a current that goes from A to B and it's steady current, then we can find the magnetic field that is generated from that. And let's assume that it goes like this. Now, what do we do? First of all, we define a coordinate system. And you define a coordinate system that does not necessarily have to be at the center. You can define it anywhere. Let's assume that I have defined the coordinate system for you, and it's here. All right, so this is X. This is Y. Excuse me, X, Y, and Z. And then I'm asking you to find, I'm giving you this point, P, and I'm asking you, and I give this point to you with coordinates. Say P has its own coordinates. And I'm asking you then to find the magnetic field that is generated at point P. So there are the following things we do. First, we connect this point until we find the line that intersects the current at 90 degrees. all right? And we call this 0. So that is important. This distance from 0 to P is like a distance r. So this is your distance OP is r, okay? Then I connect this P point with A and then also with B. And this angle here, this one, that starts from this line and ends on this one is called theta 1. And this one that starts from, so this theta 1. And this one that starts from here and ends here is called theta 2. So now I have the two angles, theta 1 and theta 2. And how can I find this? They are, theta 1 is the inverse tangent of OA divided by OP. And theta 2 is the inverse tangent of OB divided by OP. And then we use the formula and we find that B is along the phi direction in this coordinate system. And the phi direction in this coordinate system to find it is going to be, so if I take a cross section like this and I plot it, it's going to be this center. All right, this is going to be the z-axis. This is going to be my point P. This is going to be OP. And A sub phi is like that, if P is there. If P is somewhere else, it could be, P could be like here. In that case, that would be R, and this is A sub phi, okay? All right. So now you have to keep that in mind because you may have eventually to go to X, Y, and Z coordinate system. But you keep that in mind. You still leave it like this if I give you only that section of current. And then you write the next. I would not like you to derive it, which is 4 pi, in this case r, because that's what I call this distance, whatever I call it. And then it's going to be sine theta 2. I will rewrite it, and then it's going to be more clear to you, sine theta 1. So that's a formula. I would like you to know it, not to remember it by heart, but to know it when you have problems that involve sections of current. Why is that? Because if I have more than one sections and I put them together, as I will show you next, then you can solve the problem, even if it could be very difficult otherwise, by knowing this information. So I will show you how I would solve a more difficult problem, okay, using this. I will keep this on the board, and I will try to use the same here, A, B, and P, and O. Any questions before I go to something more complex? Let me see. Okay, have some time to finish that. I think this is important. Okay, so let me erase this. And I'm giving you the following problem. I have now two currents that go like this, and they are semi-infinite. So it comes from minus infinity, and then here, it comes down I, it turns at this point, I, and goes to plus infinity. And I say, I give you a point P on the same P here, on the same plane, just to make it simpler. And I'm asking you to find the value of the magnetic field there. How are you going to solve the problem? In 2 steps. First, what is different between that is that each section of the current is semi-infinite. So I have to find the semi-infinite problem. Okay? If I take this one only, let's assume go on the side to do it. In the semi-infinite case, it starts here and goes to infinity, B. Then I have a point, as I had before, point P. Let's assume that I create a coordinate system here, as I had before, X, Y, and Z. And let me take then this to cut the Z-axis perpendicularly. I call this point O. And then I connect this one, theta 1. You remember that. And then now I have to connect point P to B. But B goes to infinity. So how much is going to be theta 2? 90 degrees, because the line is going to go like that from here to meet B at infinity. All right? So this one is going to be 90 degrees. If this one is 90 degrees, theta 2, what happens to sine theta 2? 1. So this, for a semi-infinite, is going to be that. Where theta 1 is still this. Okay, that's point P. Okay. Now, I've solved this problem. Let's see how I'm going to use this here. I have 2 sections, semi-infinite. I will call for now this 1, and I call this 2, even if I know that the 2 are the same. And I'm going to solve each one of them separately. So here I say my one case is I1, other case is I2. I have to find the magnetic field due to 1, I1, the magnetic field due to I2, and then I sum up, all right, by superposition. So what I will do, I will create a little table. Okay, I1. I go here. It's like X, this is Y direction, this is X, this is Z. All right, again, what do? I connect this line, so I find 90 degrees. And then I call this O. And then I connect this, and I find theta 1. And then I find pi over 2. So practically, I say I have OP to be R. Therefore, R equals OP. And if I know this point, would I be able to find this one? If I know this point that is like 0, 5, 6, how much is this one? This is X, Y, and Z. How much is this? This point is on the YZ plane. This is Y, isn't it? Do you guys see that? Okay, I see your guys dizzy. We're going to solve a problem in a little while. So I just want you to tell me, do you see that R equals 5? Okay. How much is this one? A. This is 6. So my OA is 6. Therefore, I can find theta 1, which is the inverse tangent of 6 over 5. I can find it. How about case 2? Assume that I1 does not exist. Now I'm going here. The same thing, I have to find this point, all right, the vertical. Therefore, this one, if this is R1, my R2 is going to be this distance, which is how much? It's 6. I heard somebody saying it. It's 6. This is the Z. 6. How much is, if I call this point O prime, how much is this OA? 5. And how much is theta 1 for this case? Inverse tangent of 5 over 6. And now I have everything with one exception. I need to find out what this A phi is. Because A phi is not in the Cartesian coordinate system, it's not going to be the same for this and that. So this goes like this, down. A phi, how much is it? It's going to be plus AX. You see that? All right? It's going to be A phi is going to be AX. How about this one? The same. A phi is AX. Okay. So now you can take these, plug them here, and you can get B1, B2, and you sum them up. See how you solve these problems? We have broken down to the most fundamental bricks, and then we have those formulas available. And then we use these bricks to build up a problem that is more complex. So that's what I wanted to show you here. Okay, now that we have done this, I want you to take a break. Go and drink some water and something. I saw some of you kind of, ooh. So come back and we are going to solve some problems with magnetics for things that we have discussed. Yes. Yes.
How is it related to the del operation just now that you mentioned?
No, the del, there is no del here. The del operation is
del cross H.
del
Yeah,
cross H is a
yeah.
J.
J, right?
Yes, that's for the del.
Is this like, so this is actually
This, if you take the, not the del, if you take the del operator and integrate, you're going to eventually come with this one. Yes, so it's the result of the del operator, these ones, okay? Yeah.
And
So,
for now, all of what we're learning is all time independent, right?
yes, yes, time independent.
Okay.
Exactly.
So this is the result of integrating the del.
Yes,
Oh.
yes,
Yeah, that makes sense. All right. Thank you.
okay. Yes.
A phi. I was wondering how you got these values for A phi on I1 and I2.
Yeah, okay. So A sub phi. So I1 is like this, all right? And it's on the z-axis. So let me do it like this. This is x, y. This is x. This is z, all right? So this comes like that. If it comes like that, your phi is like this, which is positive AX. This one shows phi direction. So here, A sub phi from there, from this one, is A sub x. Here, yes, here is this. So from here, A sub phi is also A sub x. Yeah, yeah, sure.
Did you go over where you got A phi?
Yes.
That's what
he-
you're doing?
Yeah, yeah. Here.
Can you
Let's-
want to just do it when everyone gets back? I think probably a lot of people are asking.
No, no, yes. Do you want me to do it? When everybody comes back, I
Yeah,
will do that.
probably easier that
Yeah,
way.
yeah, yeah, yeah. Thank you.
The example you just talked about. So if the theta 1 and theta 2 on on the same side of the arc. I mean, if R is right here, they're on the same side. They're
Yes.
the same angle, right? They're the same
So-
side, positive.
No, no, here. So you're talking about, yes, I understand what you're saying. So let's assume that you have this coordinate system. All right, and you're here.
Yeah.
Okay. In that case, your vertical comes here.
Yeah.
All right?
Yes.
I mean, this is on the line. So this is your A. Let's assume B. This is your O. OA, OB.
Yeah.
So P. So this is your O theta 1, which is negative from the other, because we measure positives like that.
Okay.
All right? The positive theta 1 is like this positive.
Yeah.
This theta 1 is the opposite direction. So for theta 1, it's going to go so this theta 1, since we measured here theta 1 as positive, this is going to be theta 1 but negative.
Yeah.
Okay, theta 1, but it will have a negative sign.
Yes.
You have to put it. And then you connect this one, and this is your theta 2, and that's positive, because that's how we measure theta 2. Theta 2 is like this, theta 1 is like that.
Okay.
All right? So when you have the sine theta 2 minus sine theta 1, since this is going to have a negative sign, you will have to put it here, and then just use the whatever positive value you find.
All right. Got it.
Okay, sure.
The same question.
Yes.
So this is theta 1, and you're saying this should be negative theta 2.
Yes, because theta 1, when we defined it in the formula, it was like this. So that's positive for theta 1. That's positive for theta 2. So if this one reverses, you have to put a negative sign.
Question. If these were the same, wouldn't you get the zero part here?
Yes.
That's possible.
Yeah, yes. Yes.
About the boundary condition, I
Yes.
can't understand this one.
Okay.
How it can be a zero.
Because what you do this is when you have an interface, all right, and then you have epsilon mu and epsilon naught mu naught, then you take this, you take this. It's zero because there is no current. There is no current here, anywhere. Okay?
If there is no current, that's just assumption.
Yeah, if you have only two materials that come into contact with nothing else there imposed, you assume that you don't, otherwise they would have given it to you. So this is zero. So then you integrate on a surface, this, all right? And so this one, let's assume that this comes out of the board. So this is X, Z, and Y. So you integrate on this surface S, and this surface S has the normal, all right, which comes out, which is X. So you go there, and this from Stokes' theorem. If the surface has this direction, from the Heinrich, the path has this direction.
Then there is no current flow.
There is no current flowing. So then you integrate on these four sides. And then you take this to be very small. All right? And this one, and because the current here, the path goes like this, and here the path goes like that, they will cancel out. But here, the paths are longer. All right? So here what happens is, on this path, we have DL to be along the minus AY direction. And on this one, DL, so on upper, C1, C2, C1, C2, we have DL to be AY, DL. And then so if you go here, you have that HY, so this goes C1 goes to positive. I said C1, C2, C1. Okay. C2 has a negative, and then minus HY1 plus, excuse me, HY2 plus HY1 equals 0. Okay, now, this is the vector n, which is along the z direction. Okay, so I can write this A sub z cross H 1 H2. Up here I made it 2. Okay, let me see. Let me try to make it the same with your notes. So this is 1, this is 2, 1 and 2, 1, 2. Okay, we are good now. 1, 2. Okay, so this one I can prove to you, then this is equivalent to that. Because, so HZ this one, this is going to be AY. Well, it shows that Z, I mean, if this one has only a Y component, okay, let's assume that the field, I need to have more information, obviously, about the field, but this is a more, this is because I could do this along the Y direction, and I can do it along, I mean, if it's a plane, becomes more generic. And this is the best way to write it, all right? Which in fact gives you the same thing. It gives you that there is continuity. What that tells you, this one and this one, that there is continuity of the tangential magnetic field. That's what it tells you. It tells you that the tangential magnetic field is continuous.
In which situation do I have to care about the other boundary condition, like minus H1, minus H2 is equal to J something?
When there is, when I put something here myself. If I tell you that I have a J sub S here, then you have to worry about it. But if I don't give it to you, you don't.
Magnetic field intensity can be existed without the current, right? If there is
Yes. If there is current, then it's going to be related. The difference of the two is going to be equal to that current. But we're not going to do it for this class. Now, so far we don't have currents. Okay. Yeah. Okay, something for all of you. On the interface, we don't have any sources, no current on these things that we covered, the boundary conditions between dielectrics or different types of materials, all right? We don't have any imposed sources. And that's why you have a relationship that goes to 0 here, all right? You don't see any sources there because we have not introduced any sources. There are problems where there are sources, but we're not going to solve them in this class, all right? We're not going to do them now. So the boundary conditions that I gave you says that in the case of electric fields, then the tangential electric fields are continuous through the interface. The normal flux densities are continuous through the interface. In the case of magnetic fields, it says that the tangential magnetic field intensities are continuous through the interface, and the normal magnetic flux densities are continuous through the interface. Okay, so when you go to fluxes, only the normal components are continuous. When you go to fields, the tangential components are continuous. That's what you need to remember. Okay, for flux densities, the normal to the interface. For field intensities, the tangential are continuous if you have a material interface. Okay? Now, a lot of students ask me how I figured out the A sub phi for these two currents. And if this is A and this is B, and this is on this plane, all right? Let's assume that this is the ZY plane, and this is X, and this is point P. This current goes like that. Okay, when you use the right-hand rule, this one shows the phi direction, all right? So if it goes down and I go here, this one shows me the phi direction, which is what? A sub x. So for this current, A sub phi equals to A sub x. All right? This is for this one at this point. Now, let me look at this current. It goes like this. What is A sub phi? A sub x. So for this also, A sub phi is A sub x. That's how I figured them out. Okay? All right. Any other questions? Yes. Yes. So when I go down like this, when you do the right-hand rule, this one show the phi direction, all right? So when I do it like that, and the field is going to come out here like this, that's going to be the phi direction, but since P is on the YZ plane, my phi direction is going to be along the positive x. It's coming out of the board. When I go here, and I go there, it's going to also come out of the board, which is the positive AX. And that's what I have here. What I would suggest is that I would do a few more examples and give them to you because I need to finish something for the class. If we have time after what I'm going to do next, then we can do an example. All right. Okay, now, having said that, we'll go back to the boundary conditions. Okay, so remember what I said about the boundary conditions. If I have a material interface, it could be epsilon 1, nu 1. It could be epsilon 2, mu 2. And let's assume that I have electric fields. What are the boundary conditions? The tangential components here are continuous of the electric fields. And how do I write that? When I want to write tangential, I find the normal component of the surface and I write n cross. This is region 1. E1 minus E2 equals 0. That tells me that the tangential component, because it's a cross product with a normal component, so the tangential components of E1 and E2 are continuous. That's what that says. Now, what else do we know? That the normal component, this is the normal, of the flux densities are continuous. Okay? So if my electric field has tangential components, if it has tangential components, they will be continuous. If the electric field has normal components, the flux densities will be continuous. Not the electric field intensities, the flux densities. Okay, that's for fields, electric fields. If I have the same interface, but magnetic fields now excited, then the tangential component of the magnetic fields are continuous. And the normal components of the magnetic flux densities are continuous. All right? Magnetic, magnetostatics, electrostatics. Eventually, we'll see in electromagnetics the same thing apply. Same things. So, do you have any questions about this? Okay. Now we're going to solve a couple of problems on things that we said today. And I want to see. Okay. Okay, that was last week. First of all, we'll start with this problem. I will explain it to you. So I will present it. Okay. Okay, here you see is a coaxial. Now, you need to remember that the inside conductor, region 1, that shows the inside conductor, carries a current, but is a perfect conductor. So even if the current shows at the center, what do we know? The current is going to distribute where? On the surface. Then the outer conductor, which is the dark blue, also carries a current. What do we know about that current? Where is going to be distributed? On the inner surface, all right, of this conductor, even if it's shown on one place. Okay, now we put next to that metal a ferromagnetic material, means mu for this material is very high. I'll give it to you. Maybe mu is 100 times mu naught. And let's assume that the ferromagnetic material has epsilon naught and air has epsilon naught mu naught. This is the ferromagnetic. Okay? says, with respect to what you see, the magnetic field, you have to select which of the which of the selections I'm going to give you, which are the last one is slightly different. I will whether the magnetic field exists only in region 3, regions 2 and 3, and so forth. All right, one of those answers is the correct one. So I'm going to assign it to you. Let me see, do it here. Assign it. Assign, just a second. I need to make sure I'm connected, yes. Why does that? Connected. Okay, assigned as homework. All right, so now you can work on this for about 5 minutes. Yes. They are perfect conductors, all right? The conductors are perfect. We said that. Yes.
Say the data are symmetrical,
Yeah,
cancel out?
that I noticed about this formula. So I will have to go and check the book to see what he says, where I got that.
Just use the simple BOS about just to solve it. So
We can solve it, absolutely. I think it has to do with the orientation. I need to go back and look at this, and I will send me an email so I can respond to you. Because it is true, it bothers me that if the two become the same, it goes to zero. That is problematic. It's not supposed to happen. But I will need to find out. It probably has to do with the formula here and the orientation of the angles. But I'm going to go and check it out to make sure that if there is a problem, yeah. And I will do it today. So could you send me a note? So the email. Thank you, thank you. Are we ready yet? Everybody has entered? Okay, in like 10 seconds. 10 seconds. Okay, I will unassign it. And then I will show you what I see. Uh-oh. Other. Okay. So that's what you guys did. And 2 and 3 is correct. All right, so it says show correct answer.
Can you explain why 3 has, or 2 has a magnetic field?
Yes, because here is the interesting thing. All right, we need to pay attention to this one. So we have a coaxial. Let me just do the cross section. Cross section. Here is the internal conductor, and then here is the material. All right, how does the magnetic field go here? The magnetic field, since the current goes like that, it comes out, all right? It comes out, it's going to go like along the phi direction. So the magnetic field is going to go like that. Okay? And what do boundary conditions say? That the magnetic field on this interface is going to be continuous. Even if B here is much higher, but the magnetic field is going to be continuous. So if the magnetic field goes like that, it's going to be continuous here in the interface. So that means that we're going to have magnetic field here and there. However, the B's will be different. So your B here and your B here will be different. This one and this one say ferromagnetic. So this one is going to be mu H phi, and this one is going to be mu naught H phi. But there is magnetic field. All right? The B's are different. but there is a magnetic field. Yes?
submitted my answer, but for some reason it didn't pick it.
Send me a note. Send me a note.
Okay.
So I can, when I can go and modify the grade. Was it the correct one?
It was the, people can witness that.
No, it's okay. That's all right. Okay.
I'm not trying to hack the system.
I know. Thank you. No, you know why I'm saying that? Because you can get credit even for a wrong answer. I always give credit for participation. So for everybody, even if your answer is not correct, sometimes you can get, sometimes I give full credit for participation and 0 for answers, you know, for the correctness. So you always need to remember that. Okay. A next one, another one. Yes?
You said the magnetic field is continuous on that region. What do you mean by continuous?
I mean that here, when you come very close to this one, and this is your H0 phi, and this is your phi, the two here are equal. There is a continuity, so as you enter through the interface, you don't see a discontinuity there. Yes?
Never mind, it just worked.
You got it?
The answer came back like it went.
Okay, so there was a delay. Okay.
Flux is different?
Yes, by mu.
Right, okay, right.
Yeah. So this one is going to be much bigger than this one. Okay, let's go and a different one. Okay, this one. Now, having solved the previous one, this one is not difficult, needs to think a little bit before you do it. So it says a uniform and dense winding, a coil, with n turns of wire is placed over a toroidal magnetic core. So practically, you have a core, and then you put this wiring around it. That's how we do inductors, all right? We have a magnetic core, and then around it, we wind the wire. Okay. The magnetic field intensity vector H in the core is the same as inside the same coil without the core, when it's air filled. Is this true or not? It says to respond to A. One is correct, A, B, C, or D. Okay, I will assign it to you, and then I'll give you, what time is it? Okay, I'll give you about 7-8 minutes to do it. Think about it. Yes.
So I just checked my grade, but I don't know
over 24 looks like the top half didn't take my answer for Monday.
Oh, okay.
Yeah,
So you have to send me an email. Okay. All right. Thank you. Send me an email. Yeah, so in that sine theta to theta 1 needs to have a negative. It gets, because the OP has a negative. So after you finish, I'll tell you. Come, stay after we finish to explain the formula. Okay.
Okay, what he's saying is that H is going to want to stay the same, but then B and mu are going to change respectively. That's what he's trying to say.
So we have 3-4 minutes at most, all right? Ready? Let me see. There are a few more that need to enter it. We have 3 minutes maximum. Who was that? I see who is. Well, consensus, yeah. No, they are there, yeah. Yes, yeah. But not everybody has entered. Yeah. Okay, 2 minutes.
When you say the magnetic material of the core, when you talking about the intensity strength,
I cannot hear you because they are talking. Just a second.
first answer, like if the magnetic material of the core is linear, is that based off of the property of the magnetic material and like the
That's what you answered. That's correct. So okay, I am unassigning it. I will unassign it because you guys have to go. Okay. Okay, here is what you see. Always. Always. We'll talk about this next on Monday.
I have a question about this formula.
Yes.
I'm just trying to get it conceptually.
Yes.
So this part is just we're finding the magnetic field from this portion, subtracting it. But the reason why you subtract it is because it's
Yes, because of the direction. And also you need to remember when you take the signs of those, you have to be, if it goes like this down, all right, you see the direction, that's negative.
Yeah.
That's positive. Okay.
I want to submit a quiz for regrade.
Oh, so you have to go and ask Angela to tell you who of the TAs graded, and then you go and give it to them for a regrade.
Okay, thank you.
You're welcome.
Also, I want to know what happens if both data 2 and data 1 go to infinity, like the extremes of the formula.
So one is going to be 1, the other is going to be -1, so it's going to be 2. All right? So that's going to be positive, pi over 2. That's going to be negative because it's going to go down. All right? See, when you look at this, this is vertical, all right? And then we go from OP. And if this is, and Z, this value here is going to be negative, all right? Because you measure, even if you do it point A, point O, how are you going to find OA? You have to find, yes. But when you find theta 2, you need to remember that you have to find OA correctly, like in vectors. All right, so you have to look at the coordinates of this, which are negative, minus whatever this is, to find, you will find a negative number. So this is going to be, if that goes here, it's going to be minus pi over 2. All right? So that's going to make it minus plus. See? That's what I was telling. Because this one, when you find OA, you find it by like vectors. So it's like you subtract, because this is going to be given as a point, x, y, z. And that's another point. So you have to find OA as we're doing vectors. And then it's going to come out correctly. Yes, yeah. Because otherwise it would make 0, it does not make sense, all right? No, no. You have to follow that.
So about this one, so how about the outer conductor?
Yeah, the outer conductor.